On the evening of September 9th, 2010, residents of a quiet neighborhood in San Bruno, California, were going about their evening when, at 11 minutes past 6, the ground beneath them erupted. A huge fireball shot into the sky and set the neighborhood alight. Witnesses thought a plane taking off from the nearby airport must have crashed, and it took responders almost an hour to realize what had actually happened. The culprit was a natural gas pipeline, Line 132, buried a few meters deep under the city. Owned and operated by utility company PG&E, the 30-inch steel pipeline carried natural gas from Milpitas Terminal in Santa Clara County, where gas is fed into the region's major transmission lines, to Martin Station on the San Francisco Peninsula, a distribution hub supplying energy to local communities. The pipe hadn't been overloaded. The pressure that night had stayed within its allowable operating limits. But somewhere inside the steel, a crack had been slowly growing. And that night, it fractured, with catastrophic results. 8 people were killed, dozens more were injured, and 38 homes were destroyed. Could this have been predicted? Modeling how small defects grow and predicting when they'll become large enough to cause a structure to fail is one of the central challenges in engineering. One with life or death consequences, whether it's in pipelines, jet engines, or bridges. In this video, we'll dive into the fascinating world of fracture mechanics, the field of engineering used to understand how cracks grow under load and how engineers predict when materials will fail. If you take a plate and pull on it at both ends, a uniform tensile stress will develop within the material in response to the applied load. This stress is spread evenly across the material. Drill a hole in the plate, and this uniform stress field is suddenly disrupted. Stress flows through a material a bit like a fluid, and the hole forces that flow to detour around it. The flow lines crowd together at the edge of the hole, which increases the force per unit area in that region. The maximum stress in the plate at the edge of the hole reaches 3 times the applied stress. The hole creates a stress concentration factor of 3. If instead of a circular hole you have an elliptical one, the stress concentration increases even more. The more elongated the ellipse, the more tightly those flow lines are forced together, and the higher the local stress. This elliptical hole is essentially a crack, a sharp discontinuity where 2 surfaces have separated, leaving a region of the material unable to transmit any load, and forcing the load path around the crack tips instead. If the crack is sharp enough, the stress at its tip can reach high enough levels to permanently rearrange the bonds between atoms, or to break them altogether, which causes the crack to propagate through the material. And this is what makes cracks so dangerous. They create a large stress concentration that can cause a material to fail at an applied stress well below its yield or tensile strength, the properties we normally use to design structures. In theory, the local stress becomes infinite as the radius at the crack tip approaches 0. But in practice, when the peak stress reaches the material's yield strength, the material immediately ahead of the crack tip begins to deform permanently, redistributing the load and creating a region of plasticity called the plastic zone. This makes the stress state at the tip of a crack extremely complex. But luckily for engineers, if plastic deformation only occurs in a very small zone at the crack tip, the severity of the crack depends on just 2 things, the applied stress and the crack size. These can be combined into a parameter called the stress intensity factor, a single value that describes how severe the stress state is at the crack tip. For a crack in the middle of a plate, like this one, the crack size A is the distance from the center to the tip. This is half the overall length of the crack, so the total crack length is 2A. The stress intensity factor has quite unusual units, megapascal square root meters. That's because it's not an intuitive physical quantity. It's best to think of it as an engineering parameter that tells us how severe the crack tip conditions are. Larger loads or longer cracks both increase the stress intensity factor, which means more severe conditions at the crack tip, and a crack that's more likely to propagate through the material. This equation is valid for a through-thickness crack in an infinite plate, far from any edges, but real structures have finite dimensions, and cracks can take many different forms. A crack could have started at a hole, or be located on an edge, for example. These configurations are captured by a geometry factor y, which scales the stress intensity factor up or down accordingly. For an edge crack in a large plate, y is around 1.12. This crack can open more easily, which makes it more severe than an equivalent crack in the interior of the plate. For an edge crack, A is the full length of the crack, not the half length. The stress intensity factor is called Ki because it corresponds to the first of three fracture modes, ways in which a crack can be loaded. This mode, corresponding to opening of the crack, is the one engineers encounter by far the most often in real structures. The sliding and tearing modes use similar equations, but with shear stress instead of normal stress. Because mode 1's driven by crack opening, it's only activated by tensile loads. Compressive loads are actually beneficial when a crack is present, because they act to close the crack faces together, preventing it from propagating. This is why compressive stresses are sometimes deliberately introduced into component surfaces. Shot peening, for example, blasts a component with small particles, plastically deforming a thin surface layer and introducing compressive residual stresses, which make the material more resistant to the propagation of surface cracks. The stress intensity factor is really useful because it gives us a single calculated value we can use to predict failure in real structures by comparing it against a material property. That material property, called fracture toughness, is the critical value of K at which cracks will begin to propagate within the material. It represents the material's resistance to crack propagation and is obtained experimentally using a standardized test. The test involves machining a notch in a test specimen and applying cyclic loading to grow a fatigue crack in the notch to a specific length. Once the crack has reached the required size, the specimen is loaded to open the crack, while monitoring the applied force and specimen response. The value of K at which the crack begins to propagate unstably is recorded as the fracture toughness. The measured fracture toughness depends on the thickness of the material. Thin test pieces don't allow tensile stress to build up through the thickness of the specimen, a condition called plane stress. So they behave quite differently to thicker test pieces, which are in plane strain conditions, where the surrounding material constrains the crack tip and a through thickness tensile stress develops. The added constraint suppresses plastic deformation at the crack tip, so the material behaves in a more brittle way and shows a lower fracture toughness. For this reason, the standardized test specifies a minimum specimen thickness, ensuring it measures the lowest, most conservative value, corresponding to plane strain conditions. Because these tests are highly standardized, the resulting fracture toughness values can be published as reference data and used by engineers designing real structures, although additional testing is often performed for critical applications, or when a material is being used outside of previously validated conditions. Having accurate fracture toughness data is crucial when assessing cracks in real structures. Imagine you're the engineer responsible for the structural integrity of a bridge, and during a routine inspection, you discover a crack in one of the stay cable anchorages. You know the fracture toughness of the steel from lab testing performed during material qualification. Using the stress intensity factor equation, you can calculate the critical stress at which the crack would propagate. For a crack length of 10 mm and a geometry factor of 1.12, the critical stress is 252 megapascals. Combined with a structural analysis of the bridge, this lets you determine how critical the crack is, how much safety margin remains, and whether the anchorage needs to be monitored, repaired, or replaced. This approach, calculating the stress intensity factor and comparing it with the material fracture toughness, forms the basis of a method called linear elastic fracture mechanics. We mentioned earlier that the stress intensity factor approach is only valid if the plastic zone at the crack tip is small relative to the size of the crack. This is only really the case for high-strength or inherently brittle materials like titanium and aluminum alloys, high-strength steels, or glass. More ductile or lower-strength materials like lower-strength steels or some plastics deform plastically more easily, resulting in a larger plastic zone at the crack tip, which causes the assumptions of linear elastic fracture mechanics to break down. In these cases, a more complex elastic-plastic fracture mechanics approach is used. One such approach, the J-integral method, involves calculating an integral along a contour path encircling the crack tip to determine how much energy is available to drive growth of the crack. Another approach, the crack tip opening displacement method, involves measuring how far apart the two faces of the crack move at the crack tip when a load is applied. We've seen that linear elastic fracture mechanics compares the stress intensity factor with fracture toughness to tell us whether a crack is stable for a given applied load. But if the applied load varies over time, even a small, stable crack can grow incrementally, eventually reaching a critical size where it becomes unstable and suddenly propagates to failure. Paris's law is the key equation used to predict the fatigue growth of cracks. It tells us that the crack growth rate, the amount the crack advances per cycle, is governed by the range in stress intensity factor experienced during each cycle. C and M are material parameters determined experimentally. Consider a crack with a measured half-length A of 10 mm. When loaded with a cyclic stress that fluctuates between 20 and 200 megapascals, it sees a stress intensity factor range of around 32 megapascal root meters. Assuming material parameters that are typical for a high-strength steel, the crack will grow by around 0.2 mm every 1,000 cycles. The growth rate accelerates as the crack lengthens, though. When it reaches 15 mm, for example, the crack will have a larger stress intensity factor range, and so an increased growth rate. To calculate the total fatigue life, Paris's law needs to be integrated over the full range of crack sizes, all the way up to the critical size. On a log-log graph of growth rate against stress intensity factor range, Paris's law appears as a straight line. Because delta K is raised to the power m, small increases in delta K produce disproportionately large increases in crack growth rate. For m equal to 3, doubling delta K increases the crack growth rate by a factor of 8. For very low delta K values, outside the range of applicability of Paris's law, no meaningful crack growth occurs, regardless of the number of cycles. And for very high delta K ranges, as the peak stress intensity factor approaches the material's fracture toughness, crack growth accelerates massively, beyond what Paris's law predicts, and fracture becomes imminent. No real engineering structure is perfect. Welds contain imperfections. Machining leaves surface damage. And cyclic loading initiates fatigue cracks at microscopic defects that no manufacturing process can fully eliminate. In practice, the presence of cracks is inevitable. Fracture mechanics is so powerful because it gives us the tools to assess how dangerous these cracks actually are. And in doing so, it unlocks a whole new philosophy for assessing structural integrity, the damage tolerance approach. Instead of assuming a perfect, defect-free structure, the damage tolerance approach accepts that cracks will exist and focuses on making sure they can be detected, monitored, and if necessary, repaired before they reach a critical size. This approach is widely used in aerospace, where it emerged in the 1970s. Aircraft components like jet engine turbine blades or landing gear parts are inspected at regular intervals to identify and size cracks. This is done using non-destructive testing techniques like visual inspection, ultrasonic testing, or radiographic imaging. There are even methods that use special dyes or magnetic particles that are drawn into surface-breaking cracks, making them visible. Fracture mechanics is then used to predict how quickly any detected crack will grow, and whether it will reach a critical size before the next inspection. But no inspection technique is perfect. Each method has a minimum crack size it can reliably detect. So even if no crack is found, engineers have to assume that any component that passed inspection could contain a crack just below that detectable limit, and use fracture mechanics to check this hypothetical crack will remain safe until the next inspection. It's exactly this type of analysis that's used to determine how frequently aerospace components need to be inspected in the first place. The pipeline industry uses a similar approach. At commissioning, pipelines are subjected to a hydro test, a proof test where the line is filled with water and pressurized to a level 25 to 50% above its maximum operating pressure. This test helps engineers estimate the largest crack that could exist in the pipeline from manufacturing, because any cracks larger than the critical size at the hydrotest pressure, calculated using fracture mechanics, would have failed the test. Engineers can then determine the critical crack size at the maximum operating pressure, and apply Paris's law to estimate how long it would take this worst-case crack to grow to that critical size under normal operating loads. This analysis can then be used to schedule inspection campaigns. Once in service, pipelines are monitored using inline inspection, tools called pigs that travel through the pipeline and detect and size cracks. The results feed directly into fracture mechanics assessments, allowing operators to determine whether identified cracks are safe, how quickly they're growing, and when they need to be repaired. So, with all of these tools available, fracture mechanics assessments, hydrotesting, and inline inspection, what went wrong at San Bruno? Why did line 132 fail? The pipe that exploded was part of a short length installed in 1956, when a section of the original line installed 8 years earlier was rerouted. The failure originated at a longitudinal seam weld in one of 6 short pipe sections, known in the industry as PUPs, that were installed as part of the 1956 rerouting work. Unlike the standard pipe used in the rest of the line, these PUPs were formed using a non-standard welding process that introduced significant defects on the internal surface of the seam weld, which acted like sharp cracks. These defects were so severe that the pipeline would likely have fractured immediately had this section of the line been hydrotested. But the hydrotest was never performed, and the line was never inspected either. It was built before the first inline inspection tools had even been developed, so it was never designed to be piggable. The route had tight bends and fittings that wouldn't let a pig through. All of this meant the seam weld defects were left to grow under the ground in San Bruno, getting longer with each pressure cycle until one eventually reached a critical length and fractured when the internal pressure increased momentarily during maintenance work at the upstream Milpitas terminal. The operators' poor record keeping was a big part of the problem. Their records wrongly documented the pipe as having been manufactured using a process that doesn't introduce a seam weld. And they had no information at all about the steel grade, so the fracture toughness of the steel was a big unknown. These inadequate records made any kind of accurate fracture mechanics assessment completely impossible. It's often said that regulations are written in blood, and San Bruno is certainly proof of that. The incident highlighted a surprising regulatory failure that meant pipelines built before modern safety standards existed were simply exempt from them, the so-called grandfather clause. This prompted a huge overhaul of pipeline safety legislation in the United States and transformed how operators are required to manage aging infrastructure. Fracture mechanics gives engineers a powerful tool to predict crack growth, assess structural integrity, and make informed decisions about safety. And with a proper hydrotest, an inspectable line, and accurate records, it's a tool that could have prevented the San Bruno disaster. It's a theme that comes up again and again in engineering. How a part's made matters just as much as how it's designed. The materials, the process, and the quality control are critically important, whether it's a gas pipeline or a simple bracket. And that brings us to this video's sponsor, SendCutSend. They deliver high-quality custom parts, fast. If you've ever tried to get a custom part made, you'll know the pain of emailing drawings to machine shops and waiting days for a quote, only to be told it's not worth their time. SendCutSend puts an end to that. Just upload your model file to their website, or create one using their online part builder. You'll get a price instantly, whether you want 1 part or 1,000. They offer cutting, bending, and CNC machining services, with a whole range of finishing options too. There are over 200 different materials to choose from, and the service is really fast. You can have high-quality parts in your hands within just a few days of ordering. SendCutSend is the perfect supplier for your next project. Head over to SendCutSend.com/efficientengineer to upload your models and get your next project built. And that's it for this look at fracture mechanics. Thanks for watching.